So what happened with the, and Alice can help me out a little bit about the fake nail activity, or the nail rubbing activity. So you took these nails. Did everybody get to the point where they actually, how many people did the hammering of the nail? Okay. All right, so not every group did that.
Well, it wasn't in the instructions.
It wasn't in the instructions. That's why I was asking. So what happened with the nail activity? You have an actual nail and you rub it on, you rub a magnet on the nail, and what do we find? So part of the motivation for that activity is to help, so then you have this fake, what we call a fake nail, which is what Alice is holding up. So I want to hear about this because I didn't actually see what you found. What did you find? So when you shake, so the first part of this was to shake it up, and what did you find? Did it have any? Okay. Then what do? Rub the magnet on it, and then we'll bring it near the compass, and then what? Okay, so it's got some magnetism.
Just like the nail, you turned it around the other way.
Say that again?
So just like the nail, so as though one end were the head and one end were the pointy end.
It had the north and the south, like the nail.
Okay, so it had a north and south, just like the nail had. So what's happening there? Well, first of all, okay, so there's two different exercises we're doing. One's kind of an analogy for the second's kind of an analogy for the first. So what do you think's happening in the nail? I guess you're right. I mean, in some ways, this is somewhat. So what do you mean when you point to that? What do you say?
Then it becomes polar. It's like the put in positive charges and negative charges.
Okay, so let's be careful because all right, charges. So we have positive and negative charges that are part of what atoms are made of, protons and electrons. Then we have magnets. All right? It is really tempting to talk about there being charges. I mean, I'm just letting you know that in physics, the language that we use with magnets is we don't use the word charge. The reason we don't use charge is charge kind of implies that there's two separable things. There's a positive and a negative. A magnet, there are two poles here, but can you separate them?
Yeah. So it seems to me that something in there, like, I don't know if it's a particle or whatever, but that somehow you're lining them all up so that they're all going in that same way, right?
Okay.
So each individual particle has a positive and a negative. Because if you cut it in half, you cut your nail in half, all of the positive would be at one end, the negative one end. It's like they're all lined everything up.
Oh my goodness, I like what you're saying. let me draw what I think. Let me see. Let me interpret. I'll do an interpretive dance. No, I'm just kidding. I'll do that. Let me interpret what you're saying. I think what you're saying is that in this chunk of material,
and that's so
you've got.
Yes.
Is that what you're saying?
That wasn't my visualization, but yes, that's exactly. What is that? One end being positive and one end being yes.
That's before you magnetize it.
Okay, this is before we magnetize it.
What are the arrows representing?
Okay, great. What are they representing? Okay, great. I'm glad, Justin. Let's make sure everybody's on board. What the arrows represent is a magnet.
Oh, I know. Got it.
All right.
Yeah.
So this is a shorthand physicists sometimes use for magnetic. We call it a spin, or it's the north. An arrow pointed north. The arrow is pointed to the north side. Oh yeah, there's this thing. It's going to be kind of hard for everybody to see.
The other round thing again. Do we have a silver
Well, we may.
Doubtful. Not upstairs, I don't think.
there's one over there.
They're probably there because the bulbs are dead.
Well, I tell you what.
I just think those are broken.
I
Think so, but we'll see.
So here's the difference between a ferromagnetic material, like aluminum, is not going to matter no matter how much you rub on aluminum, it's not going to be magnetic. And that's because it actually doesn't have little magnetic. This is what we call magnetic domains. It doesn't have little. So iron or ferromagnetic materials actually are made up of a bunch of little magnetic domains, and they each have a net magnetic property. They all are just like a bunch of little magnets smushed together. Okay. When you rub a magnet on that nail, what it's doing is it's lining these up. Okay. So they all become lined up. That's how you make a permanent okay. And the reason they don't go back to jumbled up is because they reinforce each other. They want to be lined up. Like magnets like to line up with each other. So they reinforce each other and stay lined up. And now you've got a north end and a south end. Does that make sense?
Except in the case where you have that iron filament,
you can actually shake them apart, exactly. And this, okay, but here's another. So you guys did this to the nail, and then who hit it with the hammer? What did people find when you hit it with the hammer?
Demagnetized.
So what do you think is happening there?
You're breaking apart that reinforcement.
Yeah. Basically, it's the same. Yeah. Does that make sense?
So we tried hitting the nail on the floor sideways,
Yeah.
and it's like kind of bent the nail a little bit.
It didn't work.
And it didn't work though. It's only when you found it into the wood by the head that it demagnetized.
I don't know if I have an explanation for that. Alice, do you have an explanation for that? It seems like you're applying a random, just shaking. My assumption would be that would not matter, that you might have discovered something fantastic.
Yeah, throwing nails on the floor usually also cause them to.
Throwing nails on the
Throwing
ground?
on the floor will usually also get them to demagnetize.
Yep.
So it may have been that they
Because when you got there, maybe someone's effective.
Right.
You did pretty good.
So you did it too?
Well, I was there, and he's smashed pretty good, just flat.
And it stayed.
No, because
The one didn't work.
That's interesting. It may be just the way the energy is being transferred to the, how much energy, maybe it may seem like,
It's never uniform across.
yeah. It may have really, it may be really simple, it may have to do with how much energy is really being transferred to that. The other thing about magnets, if you heat them up enough, if you get them hot enough, way before melting, you'll totally lose your magnetism. And that's because the energy is high enough to, it's kind of equivalent to not being able to handle it. And so one way of, so one of the questions you have is, one of the questions you have is how do you create a permanent magnet? And I think giving you the sense here is that you want to just get those poles aligned. It has to be a ferromagnetic material to begin with. But if you have a ferromagnetic material, so do people know what the different elements are that are actually fundamentally magnetic?
Iron, cobalt, and nickel.
Well, magnetite's a compound. It's got iron in it. But that's right. Cobalt, nickel, and iron are the magnets. You got it. All right. Are we going to show the? Do you have the strong magnet? Right on. So this is sort of an analogy. Well, I'll let you know.
So this is basically large iron filings. And so I tried shaking it up so that they're going in all different directions, and they sort of are. Bring a magnet in.
This actually brings up another issue.
Oh, it shows the outfield.
You can't see it very well, but you can see this actually is a weird magnet. But you can see it's got some things going here and here, so they lined up. And if we get a different magnet,
That bad boy. Yeah. Oh, that's a classic.
that one worked pretty well.
So you should also, so the geometry here is something we'll talk about in a second. There's
hold the magnet longer, just if it's hot, kind of like.
Oh, you mean at one end?
Yeah.
End of the.
Oh, that's all mine.
So what is that material?
In here, there's just a little.
No, I'm sorry, the magnet,
Is this a neodymium?
Yeah.
which is,
It's an element.
so it's not just cobalt.
There's some of these ceramic. That's a good question.
Is it man-made?
So I think the answer sounds like you're asking what it's. These are really strong. Ceramic aspects. What's that? It's actually staying.
We're right on the lines. It's like we need a manifold.
I guess it just is orientation of the magnetic field.
It did something different when you set it on.
Yeah, you know what? That's confusion.
What's a different one?
Yeah, I was gonna say when you did the ramp.
That may be lining up north-south, earth, magnetic field.
This one, you know, the magnetic field is this way.
Yeah.
So this is great. I mean, so this brings up another issue that I wanted to talk about. So some of you, I know some of the groups actually try to start mapping out, taking a compass and mapping out the direction of the magnetic field. So I'm using that phrase magnetic field. Are people comfortable with that? Magnetic field? What we mean by magnetic field is a magnet is creating a sort of field. And there's a direction of the magnetic field at every point in space. Okay? This actually is showing you right here.
Is it a force? A force that's affecting all the.
Well, the field, this is kind of getting into the nitty-gritty. The field itself is not a force, it's a force if you put another magnet. That makes sense?
But that's okay.
It's like saying, is there a force of gravity in this point in open space, right? There's no, if I have empty space right here, is there a force of gravity on it? There's only a force of gravity if I put an object there. Then there's a force of gravity. Does that make sense? So there is a magnetic field, and that magnetic field applies a force to a magnet.